I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life, the universe.
This week, we are on a quest to find out more about meteorites and the building blocks of our solar system. Before that, though, could quinoa be the future of food security? Are e-cigarettes safer than smoking? And what's it like to hear again after years of silence? Hello, I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
The number of people using electronic or e-cigarettes has doubled in the last 5 years, and now it stands at about 15% of adults. Because e-cigarettes work by evaporating a nicotine-rich liquid to produce the vapour rather than by burning tobacco, some people regard them as a much safer alternative to conventional smoking. But are they safer? And might the perception of safety encourage non-smokers to take up the habit? Well, this week, 2 papers have been published examining these possibilities, one by Richard Miek, who's at the University of Michigan, and the other by Leon Shahab from University College London. Leon first.
In our study, we're interested to have a look at the relative risk of using e-cigarettes compared with standard conventional cigarettes. We looked at long-term users of these products. So these are people who had been using e-cigarettes for at least 1.5 years. And we compared their exposure to various cancer-causing chemicals with people who smoke cigarettes. We also had another control group, which are people who were using nicotine replacement therapy, who also had stopped smoking. So nicotine replacement therapy are things such as nicotine patch and nicotine gum. Compared with cigarette smokers, those people who completely switched over to e-cigarettes dramatically reduced their exposure to these cancer-causing chemicals to between 50 to 97% reduction of the levels of cigarette smokers. And the levels were very similar to people who use conventional forms of nicotine replacement therapy.
And therefore, on the basis of what you have seen from your study, what conclusion do you draw?
Well, I think the main conclusion I draw from this study is that some of the literature out there on the risks and dangers of e-cigarettes probably overstates the harm that they can cause, certainly compared with the use of conventional cigarettes, as those people who did switch over to using e-cigarettes dramatically reduced their exposure to cancer-causing chemicals.
Well, that sounds very encouraging, but on the other hand, Richard Miek, you're coming at this from a different direction. What's your perspective?
Well, we looked at a slightly different research question. So, as you pointed out in the introduction, there's a lot of debate right now about whether e-cigarettes, their use among teens, is leading them to become smokers, or whether, alternatively, kids are vaping instead of smoking. So what we did is we interviewed a group of 17-year-olds, and then we followed them up a year later. So among kids who had never smoked at the baseline, those who were vaping, as compared to those who weren't vaping, were about 4 times more likely to have smoked a cigarette in the following year. And among kids who had smoked in the past but weren't current smokers at the baseline, we find that those who were vaping were also more likely to come back to smoking, and they were about twice as likely to have smoked a cigarette in the past year.
I suppose you can't really tell, though, whether those individuals who vaped and then smoked or carried on vaping were just going to become smokers anyway.
So we actually looked at that. We had a question at the baseline: how dangerous do you think smoking is? And we had a sizable group who said that smoking was the most dangerous thing you could do. And so we looked at just those kids who wouldn't seem to be likely to go on to smoking. And even among them, we found that those who vaped were more likely to smoke. We also found that among the kids who were vaping, those who thought that cigarette smoking was highly dangerous at baseline were more likely to move away from that view. They were more likely to reduce their perceived risks of smoking as they vaped.
Now, what reasons did they give for taking up this habit in the first place?
The predominant reason for their vaping among those who vaped was that they wanted to experiment to see what it was like, and also that they liked the flavors, because vaping comes in a wide variety of flavors, some which really appeal to teens, like chocolate or cherry or bubblegum.
Leon, it seems there's a bit of a tension here, because on the one hand, we have this tool that you're saying appears to really help on the basis of your data. On the other hand, we've got Richard here saying, well, actually, it's pretty attractive to teens.
Well, yes, I have to say that I'm not entirely convinced that it's actually possible to prove a gateway hypothesis. We've looked at this in the UK. which has quite a relaxed attitude towards e-cigarettes. So we see an increase in the use of e-cigarettes among youth as well, although the use of e-cigarettes among non-smoking kids is very, very low indeed. And we can compare this with a country where e-cigarettes are not really widely available, such as New Zealand. And what you see when you compare the trajectory, that the decline is very comparable. So the proof is in the pudding in the sense that if there is indeed a gateway effect from using e-cigarettes to using cigarettes, then we would expect in the long term that the decrease in cigarette consumption and cigarette prevalence in youth should stop. But this is not the case. Neither is it the case in the US, where I think the latest data show that cigarette consumption levels and cigarette consumption is lowest since recording has started.
Richard?
Yes, that is true, in fact, that there's a historical low in the level of cigarette smoking among teens in the U.S. And our study is the one that actually was the first to report that. But actually, that's a long decline that started more than 2 decades ago. And I'd like to point out that that decline started well before e-cigarettes even existed.
Do you think then, Richard, that actually these are an evil thing and we shouldn't use them? On the basis of this, you're only seeing a negative. It's encouraging more people who were previously being extremely diligent and giving up or not taking up smoking in the first place to embrace this habit.
My main message would be that many teens believe that vaping is completely innocuous and it has no negative consequences at all. But I think if word got out that kids who vape are significantly more likely to start smoking, I think many teens would think twice before vaping and maybe stay clear of vaping devices.
Do you not think that's a risk, Leon, that it's not just kids? It could be some of the adults that we're seeing who are not smokers but might be tempted to toy with the idea of vaping because it does taste nice perhaps, or it's not regarded as so bad for you.
Yes, and it is a theoretical risk, but the data in the UK just do not bear this out. There's no evidence that I can see currently that non-smokers are taking up vaping.
So in your view, it's a good thing. It's going to help people to minimise the harms that cigarettes do.
Yeah, just to reiterate, the vast majority of people who use e-cigarettes are either current smokers or ex-smokers. And it is a sad truth that only about 50% of smokers ever manage to stop smoking in their lifetime, which means that in the UK, for instance, still nearly 100,000 people die because of smoking. And e-cigarettes are potentially a way of helping some people who have failed to stop smoking with other conventional forms of support to stop smoking. And they appear to be significantly safer than continued smoking.
Richard, last word from you?
Yeah, I'll point out that among 13 and 15-year-olds, vaping is more than twice as prevalent as cigarette smoking. Among teens, vaping has really taken off. To the extent that it is a bridge to smoking, I think that's a message that teens need to hear.
Thought-provoking, isn't it? That's Richard Mieck, and his paper was in the journal Tobacco Control. And before Richard, you heard Leon Shahab from University College London, and he published his study in the Annals of Internal Medicine. Now, the Incas called it the mother grain, while middle-class residents of Cambridge and probably also Camden are more likely to call it lunch. But for many, the quinoa plant, or Chenopodium quinoa, to give it its proper name, which can tolerate extremes of salt and drought and temperature and yet still produce nutritious seeds, could be a future lifeline. And now scientists have decoded its genome to reveal where this extraordinary crop came from and how it can handle such harsh conditions. The ultimate goal is going to be to breed these traits into other quinoa strains and even completely different crop plants in order to combat concerns for future food security. George Mills spoke to Mark Tester, who led the work at the King Abdullah University of Science and Technology, KAUST, in Saudi Arabia.
About a third of the world's food is produced under irrigation, and a large fraction of the water sources that are being used for irrigation are being depleted. We're mining a lot of the world's water, and as the water is depleted, so the quality of the water degrades and it gets saltier. And so we're actually facing a very big challenge in global agriculture because a lot of the systems that are producing food at very high amounts at the moment are not sustainable. We need to be able to increase the salinity tolerance of crops in those systems.
The amount of water is going down, and I suppose at the same time the number of people and mouths to feed is on the up.
Yes, there's an increasing demand for global food production. The UN Food Agriculture Organization predicts that we will need at least 50% more food by 2050, and yet one of the major systems that are producing food at the moment is threatened with decreasing production, not increasing production.
So quinoa, as a salt-tolerant plant, suddenly looks quite important. Using several cutting-edge sequencing technologies, Mark and the team worked out the most complete genome of the plant yet. But so what?
Well, when you've got the genome sequence, you can do a lot of things. You can have fun and do things like understand some of the evolutionary processes that have led to the genomes being the way they are. But on a more applied level, once you have the genome, then you can start to look at differences in the genome between different individuals within the species. What we find often is that if you look at a large enough number of individuals and then you characterize those individuals, look at their salinity tolerance, the way they grow, the way they produce their flowers and so on, all the traits which are important to lead to a crop that we can harvest. And you can quantify each of those aspects of the plant and then look at all of their genomes. Then what you can do is associate bits of the genome with particular traits. And with that, you can start to discover genes very, very rapidly. And that's what Sandra and the team did with the saponins.
Saponins are a thorn in the side of quinoa growers. The plant creates these bitter compounds to protect itself, but it means that to wash away this bitter taste, we need to use a lot of water, which drives up the price. But now, knowing the genome, the team have linked the production of these saponins to a specific gene, which could make breeding sweet, cheap quinoa much, much easier, as postdoc researcher Sandra Schmerkel explained.
Saponins are only really harmful in the seeds or around the seeds. So you need to plant a plant, wait for it to grow and produce seeds, and then you have to look at the seeds. So when you do your natural breeding and you're looking for the sweetness, now we have a marker. We know which gene is making it sweet. So we can look at a plant when it's very little tiny. We can take a little piece of the leaf and look for its sweetness. That's the major advantage of having the genome and knowing what genes are contributing to, say, sweetness, because we can look at them a lot earlier than conventional breeding.
It's amazing stuff, isn't it? And if you haven't tried quinoa, I can recommend it. It turns into a fabulous chili, vegetarian chili that's really, really tasty. You heard there Sandra Schmerkel and before her Mark Tester, both from KAUST, and their research came out this week in the journal Nature. Now, you're listening to The Naked Scientists with me, Chris Smith. Still to come, how Cambridge scientists are helping people with cochlear implants to recover their ability to understand speech, and the scientist who's tracking where meteorites are landing in the Australian outback so he can go and pick them up. First, though, with Valentine's Day this week, chocolate could be high on your agenda. It certainly is on mine. But can you justify eating it on the grounds that chocolate is good for you? Unfortunately, this is a bit of a myth conception, which Katani has been getting her teeth into.
Love is in the air, or at least the sickly manufactured version of love that passes for Valentine's Day merchandising. And one of the traditional gifts that people buy to show their undying affection is chocolate. After all, everyone knows that dark chocolate is meant to be good for you, so it's practically a health food, right? Wrong. First, let's take a look at where the idea that chocolate is healthy came from. The key thing is the main ingredient that gives chocolate its name and taste, cocoa beans or cacao. These are harvested from plants and then fermented, dried, roasted, crushed, ground and pounded to produce rich-tasting cocoa powder and silky smooth cocoa butter. Like the produce of most plants, cocoa beans contain chemicals called antioxidants, specifically molecules known as flavonols or polyphenols. There's a lot of interest in flavonols for bringing all kinds of purported health benefits, from boosting brain power and lowering blood pressure to helping cut heart disease or even reducing cancer risk. So it makes sense that if chocolate is made from cocoa beans, and cocoa beans contain flavonols that are really good for you, then chocolate must contain loads of flavonols and must therefore also be really good for you. Alas, it's not quite that simple. The manufacturing process from bean to bar is not kind to these chemicals. All that fermenting and roasting helps to destroy them, and sometimes cocoa is also treated to make it more alkaline, a process known as Dutching, which gives it a milder taste, but can also destroy more of the flavonols. Adding extra ingredients such as emulsifiers, milk and sugar can also mop up flavonols along the way. Another thing that makes chocolate something to be enjoyed in moderation as a treat, rather than as a health food, is all the other stuff that's in it. Flavanols are very bitter and are pretty unpalatable unless served with a side order of fat and sugar. As a result, there's more than 550 calories in 100 grams of chocolate, and that includes the really posh dark stuff. Eating too much of anything will make you put on weight, which can increase the risk of heart disease and other illnesses, and packing in a lot of high-fat and high-sugar chocolate is likely to have more of a negative impact on your health than any positive benefits from the tiny amounts of polyphenols. All is not lost if you still want to believe that chocolate can be good for you. Currently, there's a trial underway in the US testing whether capsules of flavanols purified from cocoa have an impact on cardiovascular health. Unfortunately, they don't taste like chocolate at all, don't come wrapped in a shiny box, and are way less romantic. And just to be a total killjoy, fruit, vegetables and beans are much better sources of polyphenols and other antioxidants than chocolate. Of course, there's nothing wrong with a chocolatey gift if that's what the lady loves, but let's stop kidding ourselves that it's a health food. And if you really want to give the one you love a health boost this Valentine's Day, maybe a box of fruit and veg might be a better bet than a box of chocks. Although I can't take any responsibility for any hearts broken over a bag of broccoli.
And you can't count the chocolate orange as one of your 5 a day either. Thank you very much. That was Kat Arney. And if there is some suspicious sounding science that you have come across at home, drop us a line to chris@thenakedscientist.com and we'll gladly take a look. The nerves or neurons that send messages from one end of the body to the other have fascinated anatomists for over a century. An outstanding question is, how do these cells, which can be metres long, keep all of the remote parts of the cell supplied with energy and raw materials, which are normally made in just one central region of the cell? One popular idea is that neurons contain the microscopic equivalent of a conveyor belt system which transports materials to where they need to go inside the cell. But by building a mathematical model of how this happens, one scientist has found that anyone waiting for their dinner to be delivered by a system like this would end up very hungry indeed. So something else must be going on.
I'm Dr. Timothy O'Leary, based at the University of Cambridge, and I'm a lecturer in information engineering and neuroscience. Today we're in a sushi restaurant in Cambridge, and it's one of those sushi restaurants that has a snazzy belt mechanism that allows all of the dishes to be delivered to the customers as they sit around the sushi belt.
What has this got to do with cell biology?
The cells I'm interested in are neurons, and neurons are the cells that essentially make your brain work. And a typical person has around 86 billion neurons. And one neuron can potentially connect to thousands of other neurons, and it's this connectivity that gives your brain its power. So how do neurons connect to each other? Well, in order to reach out and connect to their neighbors, they have these long, thin, branch-like processes called dendrites. So if we looked at a neuron under a microscope, it would look like a tree, a very bushy tree with lots of branches and some of them very long. If we were to zoom into this neuron and look inside one of the branches, we'd see there are lots of things moving up and down the branch. And this is because neurons are composed of lots of proteins and small components that all need to be manufactured and moved around inside the cell. So sometimes material needs to be made in one part of the cell and then shuttled along to another part of the cell. And the analogy that we use is the sushi belt, because there really is something inside the cell that moves this cargo along in a similar fashion to a sushi belt.
Effectively, you can imagine the analogy is the nucleus is the recipe book with the chef standing there cooking stuff, putting it on the plates that then go on the sushi belt, and they're carted around the cell, and the customers, the parts of the cell that need them, are going to be lifting dishes off the sushi belt at various points and using them.
That's just the picture that we have, yes.
What's wrong with it?
Life isn't really like that. At the molecular level, the movements of these particles are stochastic. That means there's a chance element in it. To explain what that would mean in the sushi restaurant analogy, let's imagine that we're waiting for a tuna roll and it's a few feet away, but then randomly the belt changes direction and starts moving the other way. And that'd be very frustrating. But what would be even more frustrating is if a person next to us who doesn't even want the tuna roll just took the tuna roll, sat it on their table for a while, and then maybe decided to put it back on the belt. Those are the kinds of things that can occur at the molecular level by chance, and it's for this reason that we can expect long delays sometimes in this transport mechanism within a neuron.
Can cells tolerate not getting its tuner roll for ages? Or actually, are you saying that this is such a significant constraint there must be something else going on because cells would not be able to put up with that?
That was actually the motivation for this study. What we did was we took experimental data where scientists had measured the movements of these microscopic particles, and then we simply took the measurements and we did the math, and we figured out how long it would take on average a collection of particles to move across a typical sized neuron. And the number turned out to be disappointingly large. It can take many hours or days to distribute cargo throughout a typical neuron. And this came as a surprise because many of us thought that cargo could be distributed on the order of minutes or hours at the very worst.
Is it not that the cell does something else, which could be it says, well, I'll tolerate some constraints of the sushi belt, but at the same time I'll also have my own local solution, so I'll make some stuff myself locally so I'm not held up. So if it's not available on the sushi belt right now, I'll make my own.
That's absolutely true. And in fact, in recent years, it's been observed that neurons do have the capacity to make things that they need locally. However, the ingredients for the things that they make locally and the machinery for making them still need to be delivered to those sites. And our claim is that that may take a lot longer than is currently thought.
I suppose what you have done is, A, to highlight some of these inconsistencies, but you've also now generated with this model a bunch of testable hypotheses.
That's absolutely true. So it's now becoming possible to peer inside a living neuron and watch these components moving around. And the kinds of experiments that people can do now can start to address some of the predictions of the model. We might find that actually neurons are far cleverer than we think, and they're able to distribute components far more efficiently than our calculations suggest. And that's why our model made the minimal possible set of assumptions. Now, if further observations contradict those predictions, then we know that actually there are parts missing to our understanding of this molecular sushi belt.
And dare I say, food for thought. That was Timothy O'Leary talking to me at his alternative laboratory at the Sushi Bar in Cambridge, and that study came out in the journal eLife. Now, hearing and understanding speech is something that many of us take for granted. In fact, you wouldn't be listening to this programme if you couldn't hear, of course. But hearing loss is something that affects huge numbers of people. It's estimated that 1 in 6 people across the UK have some form of deafness, one cause of which is damage to the inner ear, or the cochlea, where sound waves are converted into nerve impulses that the brain can then understand. For some people, a device called a cochlear implant, or as its Australian inventors dub it, the bionic ear, can be used to do the same job, but wearers often initially struggle to understand speech. Scientists in Cambridge, though, have been looking into why, and they've come up with some strategies to help, as Tom O'Hanlon has been hearing, starting with Bob Carlyon at the MRC Cognition and Brain Sciences Unit here in Cambridge.
Well, it looks a bit like a hearing aid in the sense that you have a thing behind your ear which has got a microphone in it. This microphone sends the sounds to a little processor worn behind the ear, which breaks sounds down into the individual frequency bands. And it then transmits that information across the skin using a little radio frequency transmitter to a receiver stimulator underneath the skin. That then sends that pattern of electrical stimulation to an array of electrodes inserted inside the inner ear, and those electrodes stimulate the auditory nerve directly, bypassing the damaged receptor cells which has caused the patient to become deaf in the first place.
When I'm speaking now, my voice is actually composed of many tiny vibrations happening at different rates or frequencies. You can seamlessly decode these with a helpful duo of the inner ear and the brain. So what's it like when suddenly an implant does the job of the inner ear? Mel Jewett, ambassador for the National Cochlear Implant Users Association, is one of over 500,000 people worldwide to have this implant, and she took me through her experiences.
During the first few weeks, initially everything felt very mechanical and very high-pitched. Mickey Mouse on helium comes to mind. But as the weeks went by, it became more of a natural sound to me. I was starting to train my brain and register different sounds. I was even hearing the birds singing in the morning when I walked the dog. And once a horse went clip-clopping past the house while I was sat at the back of the house, and I could hear it. It was incredible how much I was able to hear so soon, albeit in a new way. When I try and describe what it is like to hear with a cochlear implant, one way that makes sense to me is that natural hearing that we have is like an acoustic guitar, but hearing with an implant is like an electric guitar. It does take a lot of getting used to, but over time it does become natural. My dad's voice now sounds like how I remember my dad's voice. My mum's like my mum's.
Mel Jewett. So while we have the luxury of an acoustic guitar world, rich in sound and meaning, for cochlear implant users there's a tricky transition, an electric guitar world in which speech is much harder to understand. To get an idea of what this might be like, have a listen to this. Could you make sense of that? I certainly struggled.
The speech is hard to understand, but if you give people hints and clues about what they're hearing, it starts to sound a lot clearer.
This is Matt Davis, also at the Cognition and Brain Sciences unit. His research looks at how our brains understand challenging speech.
So if I tell you that the sentence was, the man read the newspaper at lunchtime, and then play it again.
I got most of that actually that time.
It sounds strikingly clearer. This is an illustration of something that's long been known about speech perception and perception in general. When you're perceiving something, you're not only processing the external sensory signals, so in the sounds in this case, you're also using your knowledge, your prior knowledge of the world and of the messages and information that you're expecting to change the way in which you perceive something. And so that's a very striking effect here. When you know what's being said, the speech sounds a lot clearer.
And do we know what's going on in people's brains when they're unpicking this challenging speech?
That's something that we've been studying a lot in the last year or two. So we've been using two different forms of brain imaging to look inside the brain and see what activity is going on when someone listens to degraded speech, just like the ones that I've played to you. And the theory that we've been developing that explains our observations is based on an idea called predictive coding. So you've probably encountered predictive texting on your mobile phone. Now, in a crude kind of way, that's a model for what the brain is doing. So the brain is continuously trying to predict the sensory signals that it's receiving. And when it processes sounds, it's doing so in a way that's guided and informed by the predictions that it had. When you know what's about to be said, you have very accurate predictions, and that's what makes perceiving the degraded speech sounds easier, is that your predictions become more accurate. They're closer to the sounds that you're hearing.
Matt and colleagues saw a reduction in brain activity when people in the study knew what they should be hearing, compared to hearing degraded speech without subtitles. The same kind of brain response was seen with longer-term learning and adapting.
Now, what we found is really very interesting, which shows that, once again, it's the brain predicting the sounds that it's going to hear that seems to be involved in that tuning in process. So people who start off an experiment finding degraded speech very difficult to understand, with minutes or hours of training get better and better at understanding that speech. And part of what's making them better is that they've improved their predictions for what that degraded speech will sound like. And that's a very useful thing to learn, because it allows you not only to understand a particular sentence, but also to understand other sentences, other speech sounds that you might never have heard in that degraded form. We think it's very similar to what's going on for someone with a cochlear implant.
So by listening to degraded or challenging speech with subtitles, you then get better at understanding degraded speech more generally?
That's absolutely right. I was reminded of this when I watched the American TV series The Wire. The characters all have a very strong Baltimore accent, which I found initially very hard to understand. Switching on the subtitles helped me understand what the characters were saying, but it also helped me tune into that unfamiliar accent. So by the time I'd watched 2 or 3 programs, actually I could do much better without the subtitles on. Having that extra support that you get from subtitles doesn't just help you in immediate understanding, it also helps with learning.
Matt hopes that using these techniques may help implant users adapt to their new hearing more quickly.
What our research suggests is that during that period of adjusting and adapting, it will be helpful for those listeners to watch the TV with subtitles on, to listen to talking books whilst reading the text of the book, that extra support doesn't only help them in their immediate understanding, but will also help them to tune in, to adjust to the sensations of sound that they receive through their implant.
It's good to hear, isn't it? That was Tom O'Hanlon, and he was speaking with Matt Davis, Mel Jewett and Bob Carlyon. You're listening to The Naked Scientist with me, Chris Smith. And now we're moving on to the main section of the programme, and we're looking at meteorites. Why? Well, one of our team, Connie Orbach, won a meteorite last year from the Science and Technology Facilities Council, the STFC. They're the main funders of space science and astronomy research in the UK. This meteorite took some time to arrive, and we were all very excited when it did turn up to unwrap it. And we discovered that it was picked up in the 1500s in South America. So Greer Jackson made it her mission to find out as much about it as she could, starting with a chat with the new owner.
I'm not going to lie, I've never wanted a meteorite before, but now I have one, I'm incredibly happy.
And it's come on quite a journey to get here, because we have been waiting in the office for weeks in anticipation of this meteorite.
I think I'd say over 2 months. It's been a long time. So I won it. It was an incentive to fill in a feedback form. And they said it would take a while because they said, we have to order it. And I was like, where from? Do you order it from space? How do you order a meteorite in this day and age? But no, I think they just ordered it from the meteorite store, which apparently exists somewhere. I'm holding it now and it's...
about an inch long, isn't it?
Yeah, about an inch long, half an inch wide, kind of bumpy. It's black, but with a silver tinge to it when you look at it in the light. And the thing that really strikes you when you get this is that it's really, really heavy.
Yeah, I'm still shocked. I mean, even though we were pretending to open it, I'm still shocked at, I thought it was packaging, like how heavy that is. I mean, that's maybe a kilo, maybe?
You think? It's definitely at least a bag of sugar. So that's how I do my measurements. So it's at least half a kilo. And it feels like a visual illusion every time you're holding it, I think, because it just doesn't match up. But my brain thinks something's wrong. And the other thing that it came with is a lovely little sign telling me a bit about it.
Dare you pronounce what it says?
So obviously I'm fluent in Spanish. Campo del Cielo.
Very good.
From Gran Chaco... Ooh, this is tricky. Gran Chaco Golamba, Argentina, found, and so this is how I know they didn't order it from space, found in 1576. It's really old. I mean, it's space rock, so it's really old, but it's like really old to this world too, which I thought was quite amazing. And then it's got the kind of what it's made of, and the main thing is iron, and that's why it's so heavy.
Do you know anything more about it? I mean, I'm thinking meteor, meteorite, comet. I'm not entirely sure I know where these things overlap.
I have no idea.
I mean, given we've all been so excited, none of us have looked anything more into it.
No, not at all. I was just excited I was getting a meteorite, but actually probably not sure what that is. I just know it's space rock of some sort.
So I'm going to make it my mission to find out as much as I can about this rock.
And if you can get some form of certificate, I'll be particularly happy.
So, a certificate and as much as there is to know about this lump of space metal as possible. Turns out I just happen to know the perfect person for the job.
I should have brought some of my Mars and Moon ones in. I keep them at home because they're precious.
Yes, she is talking about meteorites from the Moon and Mars that just happened to fall on Earth. And she is Dr. Carolyn Crawford, lover of space rock, naturally, but also an astronomer at Cambridge University. We met to compare our rocks, but first things first. What's the difference between a meteor, meteorite, and meteoroid, but also a comet and an asteroid?
Yeah, it is complicated, and astronomers do love our terminology. So you've got lots of lumps of rock, the debris that you said, floating around in the solar system. Now, if it is made of ice, so like a frozen iceberg 5-10 kilometres across smaller, we tend to call it a comet, even though it might have bits of dirt and dust within it. So comets are the icy bodies. Asteroids are the rocky debris. And we won't talk about things called centaurs, which are half ice, half rock. So they're out beyond Neptune. We won't worry about them so much. But basically, you've got your asteroids, which are rocky, and you've got your comets, which are icy. Now, a meteoroid is like a tiny asteroid. You're talking from a few microns across to a few metres across in size. So it's just debris, like the asteroids, left over or from fragments from collisions or protoplanets that's been hanging around for billions of years in the solar system and floating around between the planets, around the sun, following their own orbits. Now, as soon as that meteoroid starts to enter Earth's atmosphere, it becomes a meteor. That's what you know as your shooting star. And that's when you see it burning up in the atmosphere. It sort of excites the air molecules, and you get this trail of ionized particles which shine, and you also get the lump of rock. Even if it's tiny, it'll still give off an amazing amount of light because it's travelling quite fast. Most of them disintegrate in the atmosphere completely, but if they survive to hit the surface of the Earth, then they become a meteorite. So that's the distinction. Meteoroid when it's in space, meteor when it's in air, and meteorite when it's sitting on the ground. You get 3 basic types. The most common ones are the ones that are rocky. Then you get the iron ones, so that's iron and nickel alloy. And then you get stony iron, which have a mix of the two. This is an example of a stony one that is very nice because you see it's got a mottled appearance.
Dare I say, a bit like when you see various, sometimes I think when I'm walking down the street and you see all the little bits of rock within, what's it called, pebble dash is what I'm thinking, but in a miniature polished form. Is that a terrible thing to say?
Well, no, you're getting the idea across beautifully there. It is just speckled, and you've got these almost like little spherical, we call them inclusions, little bubbles of dust and sort of carbon material that's held within the silicate base. Did you bring this meteorite?
I did.
Okay, let's have a look. See which one you got.
See how much do you know? How much do you know about meteorites?
It's a nickel iron one.
Gosh, that's impressive. I was going to bring out the label because I couldn't even remember what it...
Sicotalin?
No.
So it's not sicotalin. It's not compo di cielo because it's metal rather than...
Oh, controversial.
Oh, it is. Compo di cielo.
I'm going to ask you how much you can tell me about this, because this is Connie's meteorite that she won, and other than giving it a quick look up on the internet, we know nothing.
This is one of the more common falls. You've got 2 very famous falls. You've got the Campo di Cielo, and this is part of the Sicotalin fall. I mean, I like this one. You can see how it's just sort of melted as it's fallen through the air. It's all kind of deformed and ruffled up. I like it particularly.
It reminds me of, do you remember the Futurists, the painters, the Futurists? You know how they had these very choppy, jagged types of paintings? That's what it reminds me of.
Yeah. Or it just looks like a parrot. If you look at the shape. But it is deformed. I mean, you look at that and you see a mangled bit of metal and you think, gosh, that metal's gone through a lot to get to be that shape. So this fell in the Sicotalin Mountains in 1947.
So this one's much more recent. Your one's much more recent.
My one was, yes, this one they actually saw the fireball through the sky. They saw the meteorite coming in and later found the pieces. Whereas the Campo di Cielo you've got there, we think fell thousands of years ago, but it was only more recently found.
To be exact, it was discovered by us Westerners in 1576 after a Spanish governor learned that the Indians believed that iron was falling from heaven. Intrigued, the governor sent a captain to find these mysterious rocks, and they were found at Campo del Cielo, fittingly translated as Field of the Sky. Since then, over 1,000 tons of this meteorite has been found, and it's believed they fell 4,000 to 6,000 years ago. But where do meteorites like these come from?
They come from a number of different places, but you're quite right. They're lumps of space rock, or if you like, space metal, that are just floating around there, orbiting around the sun. Now, some of them, especially those rocky, stony ones, are left over from the original solar system formation. So there are bits that just didn't get incorporated into being planets. Or they could be fragments of asteroids. You imagine protoplanets in the early solar system, asteroids now colliding, shattering fragments off. And then you have some which are really exciting, and they're when meteorite has impacted another planetary body. So it's something like the Moon or Mars, or say Vesta, the largest asteroid in the asteroid belt. And when the meteorite impacts that body, you send ejector out. But because things like Moon, Mars, Vesta don't have so much gravity, not all of it falls back down to the planet. It then goes out into space and starts orbiting the sun, and maybe, millions of years later happens to fall on Earth. So some of these meteorites are bits of Mars, they're bits of the Moon, or bits of Vesta.
Oh, are you about to show me a rock from Mars?
This one's a bit of Vesta.
Wow.
Which is actually surprisingly common. If you look at Vesta, I mean, this is this object that's like 500 kilometres across in the asteroid belt. It looks a bit more like a punctured football. It's got a huge sort of gouge out of the southern pole, and that's we think it underwent a huge collision some time ago in its past. So there are lots of fragments of Vesta around, and this is one here.
How do you know that?
You know, because of the mineral makeup. I was telling you, you've got all these different origins for different kinds of meteorites, and looking at the chemical composition of these rocks, you can tell a lot about whether they're pristine parts of the solar nebula or they come from bodies that have undergone what we call geological differentiation. So you've started to have that geological processing, the separation out of the metals and the sort of silicate crust. So when you hold something like your Campo di Cielo that's completely metal, that will have come from the inside of one of these differentiated bodies. So like a small asteroid that was forming or a protoplanet that was forming and before it got smashed. So you got a bit of the core part of the asteroid there. A lot of the stony meteorites are much more of the pristine debris left over from the early solar system.
Is it quite rare for this sort of stuff to fall to Earth, or is it quite common?
You have stuff coming into the atmosphere the whole time. You've got millions of meteors happening daily. It's just that most of them are tiny, kind of like, a shooting star you can get from just like a thing about the size of a grain of sand. Most disintegrate in the atmosphere, but even so you get a lot that lands on the Earth or in fact falls into the ocean, probably at a rate of about sort of 15 billion kilograms a year. There's a huge amount of stuff that is just continually piling onto the Earth. You don't look like you believed me.
Well, I was really pleased that we'd won this, and now you're telling me it's not very... I say we. Connie has won this, and it's not even that rare.
They are rare. I mean, it sounds like a lot, but it's in terms of volume and mass of the Earth, it's minuscule. Also, what you've got there is one of the metal ones. They're the rarer ones.
The reason why I ask if it's rare, and I'm glad you said it's rarer, I've got this meteorite for the weekend now. If I was to go away and sell it, what sort of price does this thing fetch?
For the size you've got there, I mean, I would guess about £60 or something.
Oh, that's pretty reasonable.
It's pretty reasonable.
Dinner out?
Well, it also depends on which fall the meteorite comes from. So you can get very particular falls where there are fewer pieces found, or it's a particularly famous fall or something about it. So, for example, a lot of people are interested in the more recent Chelyabinsk meteorite that fell in Russia. If you want a bit of that meteorite, you would get a much higher cost per gram for the meteorite than you would from things that are dime a dozen, like the Sikhote-Alin, or I'm afraid your Campo di Cielo.
Okay, I won't tell Connie.
Yeah, don't tell her that.
So why is it then that we're interested in things like 67P, and we've sent out Rosetta and we've seen Philae land on the comet? Why, though, if all this stuff is falling down on Earth all the time?
There's a lot of science you can only do when you're in contact with the astronomical body, like the cometary nucleus, and that was what was important about the Philae lander. And of course, you've got to remember comets are mostly ice, not just water ice, but also methane ice and ammonia, carbon monoxide, carbon dioxide. If you want to understand the icy part of a comet, you've basically got to go out there.
Caroline Crawford, and out there is precisely where we're going next. You're listening to The Naked Scientists. I'm Chris Smith, and this week we're investigating the origins of the material that falls to Earth from space and also made the solar system in the first place. This is what the Rosetta mission was helping to explore when its Philae lander touched down in November 2014 on the surface of comet 67P. And Greer actually got to find out what that comet smells like.
So my name's Matt Taylor. I work for the European Space Agency on the Rosetta mission that's gone to a comet. Is that okay?
That's wonderful. Tell me about the Rosetta mission. What did it set out to do?
Rosetta is a mission to a comet. It set out in 2004. It took 10 years to get to its target comet. And why do we go to comets? We go to comets because we consider them to be representative of the building blocks of the solar system. So by studying a comet, you get an idea of what the conditions were, what the material that went into building the solar system. In fact, there's material that we found from the comet by Rosetta that actually predates the sun. So it's really the primordial soup, the ingredients for that soup, and we get a picture of it by looking at this comet. We sent the spacecraft up in 2004. It chased down the comet over 10 years. 2014, we turned the spacecraft back on because we'd had a time period where we were in hibernation. We caught the comet, we landed on the comet with Philae, and for the last 2 years we've been orbiting the comet and measuring, looking at its surface structure, how it evolves in time, because the comet's really interesting in that when it goes past the sun it becomes very active. There's a lot of ice inside it that throws off tons of gas, and that peaks when you get near the sun and then starts to drop off and move away from the sun. With Rosetta, we've sat next to it all this time, observing how that stuff evolves, what the surface does, the surface changes. We think about a metre of the surface has disappeared in the time that we've been at Rosetta.
A lot has been measured and quantified and sent back to Earth before Rosetta was crash-landed into the surface of 67P. But for scientists like Matt Taylor...
It's actually the beginning. It's when, although we have been doing science already, it's when you have only time to do science, and that's when we'll be doing the big leaps and bounds and the breakthroughs with Rosetta, when we have all that time to do the science. And there's decades of work to do on this data.
So I've heard something rather intriguing in that you've done something here where I can sniff the comet 67P?
Yes, there is a number of, how can I put it, aromatic compounds on the comet that we thought would be really nice to engage people by saying, this is the stuff, right? You can visually see the tail and everything, but you can't see the gas, but you can smell the gas. And we have a mass spectrometer on board, both Philae and also the orbiter Rosetta. The one on Rosetta has picked up some fantastic stuff, sulfite compounds, rotten eggs, ammonia, are stable. So you can imagine what this comet smells like, but we thought it would be best to provide a scratch and sniff version for people to enjoy. And there have been various reactions to it's not that bad, to is it a perfume, to a child was nearly vomiting on our monitor earlier on. So yeah, it stinks basically.
Are you going to show me?
Yes, sorry.
I can smell something perfumed.
It's perfumey, isn't it? Yeah. But, I mean, the thing is, somebody's saying it's got incense. This one's actually not as bad. Maybe I'm used to it now, but it's, like I say, it's got hydrogen sulfide, ammonia, formaldehyde, methanol. There was also, we detected the comet things like hydrogen cyanide, but then you wouldn't want to put that on there because you'd sniff almonds and then pass out and probably die.
Let's give it another sniff.
Yeah. And somebody's saying incense as well.
It does smell a little bit like frankincense-y, what I'd imagine going into a meditation shop or something.
That kind of thing. Some kind of hippie head shop, as they're known in the US. I still get mothballs, so it still smells like a nan, basically. The comet smells like a nan. So I'll go generic. There you go.
So other than, getting a whiff of what a 67P smells like, what would be the best thing to the outcome here? I mean, surely we're not going to unpick what the entire origins of our universe and solar system are.
Well, with Rosetta, we are starting to do that. Really, what we've got from Rosetta by spending the 2 years there, by landing with Philae and adding all of this stuff together, we're just starting to scratch on the surface of the capability of the data from this mission, to the extent that we think we have identified primordial building blocks in the comet that actually are probably common with other comets, that we can say we think we know how comets were made now. And that's quite a big result, and that the implications there lay in with the general solar system evolution. So that's what we have to look forward to. So I wouldn't say we've solved everything, but we've done a good job, and there's a lot still to do, and I'm pretty excited by the science that's going to come out in the next couple of years with Rosetta.
We shall just have to wait with bated breath then. Back to the meteorite though. Having carried this around with me for the last couple of weeks, and no, I didn't flog it, I got rather jealous. I want a meteorite, which left me frantically looking around on the internet about how I could get my hands on one. And I found something on Cambridge University's Institute of Astronomy website. It's a Q&A thing where people can ask a scientist a question, and conveniently Carolyn Crawford also helps with this. The question reads, "Hello there, I was wondering if it's possible to test rocks to see if they're from space. I ask, and this is true, whilst I was gardening today, a rock fell into my wheelbarrow. It sounds crazy, but it did happen. The object is black, looks like coal, and is very light, I suppose pumice. If it didn't fall from the sky, I would say it's a piece of normal earth rock. But as it came from above, I'm very curious."
I don't remember reading that. What did they say in response?
The response was something along the lines of, I doubt it very much because they're normally very heavy and that sort of thing. But it tickled me. I read it and it tickled me to no end that, the idea of it falling in someone's wheelbarrow.
A couple of years ago, there was a lovely story of a French family who, as in the way of the French having their holidays, vacated their house in Paris, went off for their summer holiday. And when they came back, they thought, that's strange, our roof is leaking. and they sent someone up to fix the roof. And what they found was that the hole in the roof was created by a little meteorite that had just punched a hole through the tile and got embedded in their sort of insulation in the roof. So they had their own little meteorite that had hit their roof. I think that's quite cool.
Yeah, really cool, really cool. I imagine lots of people have got lots of interesting stories about how they've come into... I mean, I was really excited by ours, but I suppose it's not the most exciting way to come across a meteorite.
No, the most exciting thing is when you actually see the event. You see the fireball, and a fireball is just when you've got a bigger lump of rock that as it disintegrates, it produces a lot more light, and often they will just break into lots of pieces and you just get a fantastic show as they fall to earth. Sometimes, if you're fortunate enough to see one of these, you, especially nowadays with security cameras, and you get all these serendipitous sightings of the fireball, you can track its orbit, you can track its path through the atmosphere, you can predict where it's going to land, and then people can go out and look for the bits of rock. So, for example, this has been done places like Canada, where across the country people saw this fantastic fireball in the sky, and then when it had landed, they tracked it down to where it had landed. They went out to look for it, and being Canada, it's a land of lakes. All the lakes are frozen, and you just looked at the lakes, and they were almost like just fragments of meteorites scattered all over the ice in these lakes. I mean, that must be so exciting to see those.
Incredibly exciting. And there's a project called Desert Fireball that looks to track these events back to where they came from. And it involves taking a selfie with a meteorite, if you're quick enough. Georgia Mills sat down with Curtin University's Philip Land, who came up with the idea.
It's a project where we've put out lots of little kind of observatories across Australia, and they look at the whole sky and image everything that comes through the atmosphere. And what we do then is we're able to triangulate the orientation of anything coming through, track it back to where it comes from in the solar system, and forward if it lands to where it lands. We get its orbit and we get a full position.
And are you also trying to use the great power of the masses to help in this project?
Yes, we are. So if you see a fireball, you can pull out your phone and hold it up to the sky, click on where it started, where it ended, the colour. You can log all of this stuff and then blip us that information. And that also helps us triangulate it. If we get enough data, and we can tell you your fireball came from out beyond Mars and hit the top of the atmosphere at 20 kilometres a second.
I guess it's people's first instinct anyway when they see something incredible in the skies. Get your phone out.
Get your phone out, exactly. So this actually gives you a scientific purpose to get your phone out.
Anyone taking meteorite selfies?
Well, we've not actually had that yet.
When you get this data from all your observatories and maybe from people as well, what do you do? How do you go and find the asteroid?
That's the hard part. So we build this wind model, and then you head out in the middle of nowhere with a team of 6-7 people, and you've just got to be very optimistic and perky for a week and try and keep them going while you don't find it, until in the end hopefully you do, and then you will have a bottle of wine or several. Yeah.
And I believe you've got something you have found with you here.
So this is a meteorite. This was the first one we found. This kind of proved that it worked. It's called Bumbura Rock Hole.
Can I touch it? It looks and feels a bit like a sort of shiny lump of coal. Once you have this rock and you've used your tracking to work out where it's come from, what do you do with it once you find it?
We'll look at the isotopic composition, the chemistry. We'll use microscopy. We'll do kind of CT scans of the thing. So there's a ton of analyses that we can do to kind of build up a picture of its whole history.
What's the furthest you've ever got anything from? Would any specimens from the Kuiper Belt actually fall to Earth? Is that something you're looking for?
We go through streams of comet debris on a regular cycle, which are meteor streams. Most of that stuff is dust, which means that it'll almost all burn up in the atmosphere, really high up. But some of it is chunkier. And there's one stream in particular, the Geminids. It's a comet that's been cooked up a lot by many close approaches to the sun. So it's certainly not in as good shape as it was originally. But what that's done is the material is denser now, and it looks like some of that should be able to make it to the Earth's surface. So my kind of holy grail, if we were ever going to find anything, would be that we'd see something come in We'd put those images together, we'd calculate its orbit would match one of these Geminid meteors, and we'd work out that it had landed, and we'd go and pick it up, and that would be absolutely incredible. It wouldn't be nearly as pristine as some of the others, but technically that's possible.
Best case scenario, what could you learn from a meteorite that had come all that way?
Oh, wow. That's a really good question. I mean, best case scenario, I got into planetary science and studying meteorites because as a geologist, it felt like a lot of the things in geology, we'd worked out pretty well. We know the kind of grand unifying theory for geology, plate tectonics, and it's been kind of a case of putting the finishing touches to that, really. But in terms of what happened before planets got made, or how we made planets, or why the Earth has the composition that it does, we really have very little idea. So if you ask someone, okay, how do you make terrestrial planets? How do you get a planet that's got a nice mix of rock and ice and water and organic material? Well, no one knows. There's dozens of different options, and I found that really, really exciting, as kind of a young researcher. So that's why I got into it. So in the best possible case, we'd work out why we have terrestrial planets in the inner solar system, why that happened. And that would be quite exciting to know that.
Phil Bland. And speaking of things crashing into the Earth, for Question of the Week, Tom O'Hanlon has been investigating this query from Faye.
I heard that due to an asteroid, a giant crater was formed 66 million years ago, and the debris wiped out the dinosaurs. I have also been told that birds are dinosaurs. So, how did the birds survive?
Faye's quite right. Although your roast chicken might not look particularly dino-esque, scientists are agreed that birds are direct descendants of a group of small feathered dinosaurs. So what about this asteroid? What actually happened? I asked David Norman from the University of Cambridge.
The overwhelming evidence suggests that there was a massive meteorite impact at around about 66 million years ago. And the explosion creating a huge set of environmental problems, in a sense. Lots of water vapour, lots of chemicals introduced into the atmosphere, completely messing up our ecosystems. The equivalent, I suppose, in terms of modern theorising, is a nuclear winter. It's as though there was a nuclear holocaust, and it's sort of almost destroying life on Earth, but not quite.
Given that we're still around today, some things clearly made it through. So was there a pattern to who lived and who died?
Certainly on land, anything over a metre in body length probably went extinct. It may be something to do with the biological nature of small organisms. Most of the big ones are, you could say, top of the food chain, and perhaps more specialist and most susceptible to environmental disturbance. That's certainly the pattern we see in ecology today. The things that have most chance to survive are the scavengers, the small, fast-reproducing sorts of organisms. And in a way, the lizards, the snakes, the small crocodiles, the small mammals that were our ancestors, and various other little organisms seem to have got through because they were the most resilient to environmental disturbance. The little, insulated, feathered, bird-like dinosaurs also got through, and therefore the dinosaurs did survive the extinction. But they survived because they were small bird-like creatures rather than big, scary dinosaurs.
Which I suppose we're fairly grateful for today.
Yeah, I guess so, yeah. Although, some of us would actually quite like to see a dinosaur in the flesh at full size. The nearest we'll ever get to it is something like an emu or an ostrich or a rhea. Their feet, especially with something like a rhea, have those three classic talon toes, which look very, very reptilian, and actually, wouldn't be so far different, except in scale, from something like the feet of a dinosaur, like T-Rex.
There you go, Faye. I hope that managed to meet your expectations. Next week, we'll be looking at David's question.
If we put a mirror 500,000 light years away and reflected Earth, could we see what Earth looked like 1 million years ago?
Well, you've now got a week to reflect on that, and we'll be back with the answer, including your suggestions, which you can send to me to chris@nakedscientist.com or to our Facebook page in the meantime. That's it for this week. Thank you to Greer Jackson and Georgia Mills for production, and do be sure to join us next week when we'll be asking, are we on the brink of reversing the HIV pandemic? We'll be investigating how a new drug regime is dramatically cutting infection rates. Join us to find out how. The Naked Scientist comes to you from Cambridge University and is supported by the STFC, the EPSRC and Rolls-Royce. I'm Chris Smith. Thank you for listening, and until next time, goodbye.